Okay, so hi everybody. So today I want to talk to you a little bit about atomic physics, which is something about how atoms work as a fundamental thing. Now, the textbook goes into a lot about the history of how we understand the structure of atoms. I kind of figure many of you guys have got that in other classes, and so I'm not going to be going into that in great detail here. The basic picture of the atom that I think most people know is that there is, of course, a very dense nucleus, which contains the protons and the neutrons and is fundamentally positively charged. It is surrounded by a cloud, a much larger cloud, of negatively charged electrons that are basically held in place by their electrostatic attraction to the nucleus. And different types of atoms have basically different number of protons in their nucleus, and that affects the configuration and structure of the electrons surrounding them. Now, one thing I do want to highlight, which is important, is the nucleus is a tiny fraction of the atom as a whole. A typical electron cloud is about 10 to the minus 10 meters across. So something called an angstrom or 0.1 nanometers. By contrast, the nucleus is 10 to the minus 15 meters across. So the nucleus is a very, very, very small part of the atom. It contains most of the mass, but it contains a very small fraction of the volume. And there's a variety of experiments that show this to be the case. But what it means is that a lot about the way an atom works and how it interacts with other atoms and even with light is mostly involved in its electrons, because its electrons are much more broadly distributed. When atoms interact, they interact through their electrons. And again, this is, the basis of chemistry, etc., which it's a good thing to keep in mind. And what I want to focus on today is, why are the electrons distributed around these atoms the way they are? And the reason I want to focus on that is it directly relates to the things we talked about in the previous video, which is basically, this is a representation of quantum mechanics. And to kind of set this up and make this connection clearer, I want to go through a few points about atoms that make them weird and to understand, what causes this weirdness. The specific thing I'm going to ultimately be focusing on is a peculiarity of how individual atoms interact with light. As you know, light comes in a variety of wavelengths, which correspond to a variety of frequencies, which correspond to a variety of energies. Now, certain types of sources, like incandescent bulbs, etc., can produce light at all wavelengths. So if you send it through a prism, you get some amount of red light, some amount of yellow light, some amount of blue light, etc. But if you look at the light from specific types of atoms, that's not what you see. You see light at only certain frequencies, only certain colors. And which colors you see depend on which type of atom you're looking at. Hydrogen produces a red line, a blue line, and a couple of purple ones. Sodium famously produces very strong yellow light, but nothing much else. Each particular type of atom produces light with very specific spectra, with very specific signals at only particular wavelengths. And again, this is just what happens when you heat up or excite hydrogen and just see what type of light it produces. What I'm trying to explain here is, why is this? And the reason that atoms do this is because their electrons are in quantum mechanical states surrounding these nuclei. So to try and explain this and try and make it clearer how this happens, I want to just do a bit of analogy busting here. Again, most people have seen this and learned that it's wrong. There's pictures where you have a nucleus and you have the electrons shown whizzing around it on orbits. Pretty much, many people are shown this picture and told that it is wrong. What's important to understand is how it's wrong, because understanding how it's wrong is really relevant for understanding what's going on here. So what we're doing is we're going to contrast, or we're going to compare and contrast the properties of electrons around a nucleus to the properties of planets orbiting a star, like the planets in the solar system orbiting the sun. Now, in terms of the basic physical forces involved, these aren't that different. The electrons are held in place around the nucleus by basically Coulomb's law. It's a little more complicated than that, but it's essentially Coulomb's law. The negative charges want to get close to this positive charge. In the solar system, the planets are held in orbit around the sun by their mutual gravitational interaction. And both of these forces are actually structured in very similar ways. So in terms of the forces, they're very similar. But there's an important difference. The planets are on well-defined trajectories. They have real, what are called orbits. You could basically say that Earth, if it's currently here, will be somewhere else along this circle sometime in the future, and you can even calculate where it is. Its trajectory and position is completely determined as a function of time for a long ways in the future. Now, there are caveats to that, but that's a good enough statement. The electrons, since they are quantum mechanical things, and we've already seen evidence for that from the fact they undergo double-slit diffraction, that fundamentally doesn't work. They do not follow a well-defined path around a nucleus. Instead, they are in what's often called an orbital, which means that there's a probability distribution that tells you the likelihood of finding an electron at any given location around the nucleus. And there are various ways to represent this. This is one I found where basically how bright the color is depends how likely it is. It's fairly likely to be found close to the nucleus. It's less likely to be found further out. But it's not something that you have a predictable trajectory. It's something that could be anywhere. So that's the distinction that's often made. But we want to go a little further than that. The thing is, there is another commonality even between these orbitals and these orbits. And that has to do, again, with energy. The planets in the solar system, they're moving around the sun. They have kinetic energy. They feel a force from the sun. They have potential energy. Turns out, even if the planet doesn't stay the same distance from the sun, the combination of its kinetic energy and its potential energy is mostly constant. Each planet in our solar system, as it goes around the sun, has a constant, what might be called orbital energy. And different planets have different orbital energies. If we remove and have different orbital energies, the thing to note is if we add energy to a planet or remove it, we can cause the planet to move closer or further from the sun. So it's not just that these have different energies, they have systematically different energies. To orbit far from the sun, you actually have to have more energy. If you lose energy, for example, if Mars suddenly slowed down for reasons, it would lose energy and fall in towards the sun. It would get closer. So we have Mars, which has the most orbital energy of these planets, then Earth, then Venus, then Mercury. So each of these orbits is not only a distinct trajectory, it's a trajectory with a distinct amount of energy. Now, these weird orbitals for electrons around nuclei, they also have different energies because different electron distributions can keep the electrons at different distances from the center. So for example, this state, shown in yellow, has the electron pretty well confined to close to the nucleus. This configuration, this distribution, allows the electron to get further out. Each one of these has a distinct amount of energy, but this one is higher energy than this one. If this one lost energy, the electron would end up closer to the nucleus and you'd get something like that. So just like in the solar system where different orbits have different energies, different orbitals or different states have different energies here. But again, there's a difference. We can imagine, it's a hard experiment to do, an orbit with any energy. If we, for example, slowed down Mars a lot, we could have it fall into the sun until it was close to the orbit of Mercury. But we could also make it move to the orbit of move to the orbit of the Earth, or anything in between. It just matters how much force you apply to Mars. You can make it move in a lot, you can make it move in a little, you can move it anywhere in between. It's a continuous variable. The orbital energy of a planet is something that's continuous. That is not the case for these orbitals of electrons. Electrons do not have the option to be in any probability distribution. There are only distinct ones. There are only certain ones that are allowed to exist for any length of time. These particular configurations are the real orbitals, but are also more generically called states. And they are a discrete number of them. There is a large number of them, but you can't create a system that's like halfway in between the two distributions I've shown here. You're not allowed. Now, that is again a thing about quantum mechanics that's weird. It's like, why can't I do that? I want to do that. I have infinite technology and money. Can't I do that? And here's where the rules of quantum mechanics come into play. And I do want to try and explain this distinction a little more clearly because it's important. In principle, you're right. You can create any distribution function you want. If you could imagine putting a little shell around the electron so it's certain to be in some region just off the center of the nucleus, you could do that. But, and this is the key thing, arbitrary distributions of probability aren't stable. The equations for how these probability distributions change with time, those rules of quantum mechanics I talked about at the end of the last video, say that that distribution will start to change and actually change very rapidly. So if you start with charges, say, on one side of a nucleus, they'll drift over to the other side and do all sorts of other things. As that distribution is shifting and changing around, that's equivalent to a moving charge. It's going to basically release energy until it's in a configuration where the probability doesn't change. Those are what are special configurations. There are just a few configurations where the probability distribution does not evolve over time. Now, what are those configurations? Those are various obnoxious functions that are basically defined by basically Coulomb's law, and some extra complications due to the fact you're trying to put multiple electrons in orbit around these things. So, and again, I'm trying to avoid all the scary math, which involves calculus anyway, but the basic thing is there are certain distributions where the wave function of the electron basically gives you a constant probability distribution. And forcing that to happen turns out to be a very stringent constraint, and there's only a discrete number of those configurations that exist. So, for example, these are just to say the probability distributions represented in different colors. Again, either yellow or blue indicates where there's lots of particles, and regions in between are where there are little particles. Regions that are bright yellow or bright blue are regions where there's a high probability of finding the electron. Other regions are where there's very little. And blue versus yellow has to do with the sign of the probability distribution, the sign of the wave function, which is the thing you square to get the probability distribution. So either something that's bright yellow or bright blue has lots of stuff. So you have distributions that are symmetrical like these. You also have ones that are not symmetrical like these. These are all allowed states. But the thing is, you can either have a distribution that's about this wide or one about this wide, but nothing in between. And if you want a really good explanation for why you can't do anything in between, I'm sorry. It turns out the math forces it. I can't give you a quick intuitive explanation for that. It is related to wave properties. It's basically a mode of the electron's wave function. Okay, so these are the only, so there's a countable number of discrete states electrons can have. And these are the only ones that can last for a significant length of time. You can create other probability distributions, but eventually they'll do things and wind up in one of these states. Sometimes you can make it end up in some combination of two, but that's fairly rare. Now, just to also say, these are the states for an electron around a nucleus. This is relevant for hydrogen, which has one electron in orbit around one proton. One electron in a probability distribution around one proton. If you have multiple electrons, then they start interacting with each other. And that makes the distributions even more complicated, and people usually avoid drawing those. So, but these are the allowed things, and each one has an energy. And this gets to how we represent these states. In principle, we could just draw them like we did, but that's really hard because what I'm drawing here are kind of weird projections of a full three-dimensional distribution function, it's really hard to draw properly. And different people do it different ways, and it's awkward. There's lots of cases, and for lots of things, I don't care what the actual distribution is. I only care about some of the properties of these states. For example, one property I often care a lot about is the energy of these states. And so some states have lower energy, some states have higher energy. The way people often represent these systems is with what's called an energy level diagram. What this is just a plot of energy on the vertical axis, and you mark on that vertical axis the locations corresponding to the energy of every one of the states. So in this case, we have the lowest energy state where the electron is hanging out really close to the nucleus, which is here. We have another state where the electron is able to be a little further from the nucleus here, and we have another energy state where the electron is further from the nucleus here, and we could draw other ones like this. This just shows what are the energies of the allowed states. And just to say, what you'll notice here is the numbers are negative. Why are they negative? Well, remember, energy as an absolute value rarely means anything. What's relevant are energy differences. And the classic way to do this is the case where you can take where the electron can get all the way to infinitely far away from the atom corresponds to zero energy. If it has zero energy, the electron can just fly away. Each of these states keeps it from doing that. And so each one has a lower energy than zero, so it's negative. Ones like this, which are fairly far out, have a slightly negative energy. Ones that are more compact have a lower negative energy. Also notice, these energies are in electron volts. That's because this is the energy of an electron. So doing joules is kind of a pain. So this is often expressed in electron volts. So each of these lines represents a state, represents one of the energies the electron is allowed to have. So that's what the horizontal lines are. What's the vertical lines? Well, those are transitions between states. Here, and this is where things get kind of interesting. If we have a high energy state, like say this one, and by the way, we label these with various letters and numbers. These are, N is the thing that primarily controls energy, and there's 1, 2, 3, 4, 5, and it gets up to infinity by the time you get to 0. There are other numbers that indicate things like angular momentum, which are L, or other parameters. They're just different ways to catalog these different states. So each one of these lines gets a name or a set of numbers that identify it uniquely. Okay, but if you have something with a high energy, like say maybe this line at minus 1.51 eV, that thing could transition to a lower energy state, like this one at minus 3.40, this guy. If it does, the electron loses energy. The atom loses energy. But energy by its nature has to be conserved. So if the electron lost energy, something else has to gain it. Where does that energy go? Well, as this transition is happening, the electron distribution is changing. That's equivalent to moving charges. That will create an electromagnetic disturbance. What it will produce is light. And the easiest way for it to do this is for the transition to produce a single photon's worth of light. Why a single photon? Because that's the most efficient way for this thing to change. Now, the thing to note is energy is conserved. So that one photon, which I show here as a big green arrow because photons are weird, must have an energy equivalent to the energy difference between these two states. So if we start here at minus 1.5 and end up here at minus 3.4, we've lost about 0.9 eV worth of energy. This guy, this photon, has 0.9 eV worth of energy. Now remember, photon energy goes like frequency or wavelength. So what that means is that that particular light, which is going from 3 to 2, which is, let's see, that is the Balmer series. I believe it's this one. This one produces light with a particular wavelength. Turns out to be 656 nanometers. If we had a transition from 4 to 2, that's a bigger change in energy, which means a higher frequency, which means a shorter wavelength. So it's this guy. If we go from n equals 5 down, we get an even higher energy. But the way these things are stacking, they're getting closer and closer together. So that's what we get. We get a series of lines that correspond to different transitions. Similarly, if we go from n equals 4 to n equals 3, we have this one. That one drops here. It's a smaller energy change, so it's a longer wavelength. And if we go from, say, n equals 2 to n equals 1, we drop a full roughly 10 eV. This produces what's called a line in line. This is something in the ultraviolet and is, around 122 nanometers. So the thing is, if you know what the energy levels are, you calculate the difference between all of them, you can predict where all of these are, where all of these transitions are in energy, and where all of these transitions are in wavelength. Now, again, the book spends some amount of time using a kind of toy model for the hydrogen atom that more or less reproduces all of this. And it turns out, yeah, you can actually calculate where the lines are for hydrogen with that method. The trick is doing anything like that for any of the other atoms which have more than one electron turns out to be really hard, because what you have here are multiple electrons that are interacting with each other and also have weird ways they interact in terms of their probability distributions that basically make this pattern of levels much more complicated. And it turns out often, you can calculate them sort of from first principles, but it's a little hard. But there are, again, a series of levels, and these are just transitions between those levels. And in fact, this is one of the reasons you can use spectra to figure out what something is. Since if you see a series of lines, you know this atom has a series of levels. And since each atom is just some number of electrons in orbit around some nucleus, you can start to go, oh, okay, this is something with the right number of electrons and the right number of protons to be calcium or mercury or sodium or anything else. This is why you can use spectra to be diagnostic. So, that's pretty cool as far as I'm concerned. And the other thing to understand is it can go the other way. If you have a low energy state, like say something in the ground state or maybe n equals 2, it can turn into something with a higher energy if it can absorb energy from some source, like an electromagnetic wave. Now, the thing is, the only way to do this transition to go from one state to another is if this will only work if the energy of this photon it's going to absorb is equal to the energy difference between these two states. So the light has to have the right energy, the right frequency, the right wavelength to make one of these transitions. Otherwise, this interaction isn't going to happen and the light's just going to sail through. So this not only applies to, what kind of light the atoms produce if they're in excited states, but also the kind of light they absorb. And just a pretty example of this is this spectrum of the sun. This is just a spectrum showing the brightness of the sun as a function of wavelength. Starts up here in red, goes across, comes less red, turns to yellow, turns to green, turns to blue. That is from the background spectrum is from the really, really hot interior of the sun. But what you see are dips at various locations. Those dips are, again, locations where atoms in the sun's atmosphere are very efficient at absorbing light because the energy of those photons is exactly right to produce a transition between two energy states. So again, there's two things here in the yellow that are due to sodium. There's this guy that's due to hydrogen. There's another one over here that's due to hydrogen. There are things due to iron. When people went through this, they found a lot of elements that they knew about, and, for example, one they didn't. There was one type of atom that hadn't been seen before. They called it helium, for sun atom. This is one of the ways it was found. And again, it was just a pattern of things. You could figure out, oh, these lines don't match. So what is the structure? How many nuclei does it have? You can figure that out. This is why I wanted to focus on this. This is where quantum mechanics is essential for understanding the chemistry of things. And I mean that literally, because these sorts of rules are what underlie all of chemistry. Now, I'm not going to go and say, well, therefore all of chemistry is physics. Understanding the details of these interactions is really hard, and they are not at all intuitive. But whenever you have molecules where you have multiple atoms joined by chemical bonds, these same rules are working. If you have multiple protons or multiple nuclei close together, the distribution of electrons around them are in a series of fixed states. These are various ones I found on Wikipedia for acetylene, C2H2. So you have two carbon separated by two hydrogen. There are electrons that have states that surround all of these different nuclei. And what those configurations are, again, depend on the same rules of quantum mechanics. And where they end up is critical for determining whether these electrons are in places where they can hold the atom together or cause it to split apart. This is the basis for, sharing electron orbitals, et cetera, like that. All of those rules are basically from this. And again, that's for the entire field of chemistry to properly understand it, but the basic idea works. Furthermore, since you now have electrons interacting with a lot more atoms, and also you now have atoms interacting with other atoms, there's now a lot more potential for states to exist. There's many more options. And that leads to much more complex spectra. Because now you don't just have transitions between one electron state and another, you also have transitions between how the atoms are distributed relative to each other, how they move on average relative to each other, et cetera, et cetera. And this gives rise to complex spectra This is, because I'm an astronomer, a spectrum of Saturn's moon Titan. What you're seeing here are spectra associated with different molecules. Here's acetylene. It has one strong band here, but lots of other little bands that correspond to different energy transitions. Here is C2H6, here's methane. All of them have different patterns. And this is why, because fundamentally, once you've set up the protons, more or less, you've created an architecture that basically constrains what kind of energy states are allowed. Now, just to wrap this up, there is one other case I want to discuss, which is relevant from a health standpoint. You could imagine what happens if I have something in a low energy state and hit it with a really high energy photon. If this photon has a high enough energy, more than say 13.6 eV, then it can take an electron that was in orbit around, that was in a state that was confined around the nucleus, and put it in a state that could get it anywhere away from the nucleus. It could give it enough energy to escape the nucleus. So if this thing has enough energy, more than 13.6, that electron goes from being bound to the nucleus to being completely unbound. This is ionization. Now, to do this again, the photon needs enough energy. That means its wavelength needs to be short. Its frequency needs to be high. This is typical of things like UV and X-rays. Ultraviolet light and X-rays can do this. Infrared, visible, and microwave or radio have a hard time doing this because that requires multiple photons worth of energy to get into the electron, which is hard. This is why UV light and X-rays and gamma rays can ionize atoms or equivalently break chemical bonds. They can do chemistry in a way that longer wavelength, lower frequency light just can't. This is why things like UV and X-rays can damage cells and affect things. So hopefully this gives you a little bit of an idea about why quantum mechanics is relevant to atomic physics. Next time we'll talk a little bit more about what's going on within that nucleus. Thanks.